All right, welcome back, everybody. Today we're going to be taking a step back into Chapter 6. In particular, we're going to jump back to Section 6.2, and we're going to use what we just learned about the right triangle trigonometry to do more with inverse trig functions. It's kind of funny because we could have done this back in Chapter 6, but in my experience, it's much easier to answer these kinds of questions when you have right triangle trigonometry at your fingertips. So let's get right to it. I'll pull up the slides. Here we go. Okay, so now that we've developed right triangle trigonometry, it helps us do this process much easier. So we can evaluate inverse trig functions more easily with these techniques. The other thing is this, I forgot to mention it on the slides, but you're going to use this technique a lot in Calculus 2. So in Calculus 2, there comes a point where you're doing integration and you learn about something called trig sub or trigonometric substitution. And when you do trigonometric substitution, you essentially need to use a right triangle to recover information about the substitution that you're making. That process is identical to what we're going to do in this section right here. So when you get to Calc 2 and you're in that section, just remember this is exactly what you're going to do. Exactly what you're going to see here. So one thing to keep in mind here is that the definitions of the inverse trig functions are still the same. So if you go back and look at that section again, what was it, 6.1, we introduced these as being the angle whose sine is this or whose cosine is this, et cetera, et cetera. So that's the question that you want to say in your head every time. Oh, this is the angle that has a sine value of blank, or this is the angle that has a cosine value of blank. You're still going to use that idea. So what are we going to do differently here? We're going to construct a right triangle that exhibits the relationship that's given to you. Then we're going to find the length of the missing leg or hypotenuse, and then we're going to use that new triangle to evaluate the trig functions. Another thing that I want to point out is that the restricted domains of the trig functions are still in effect. If you remember back in 6.1, we had to restrict the domain of the trig functions in order to even define the inverse trig functions. So those restrictions are still in effect. Just a quick reminder, for sine, the restriction was from negative pi over 2 to pi over 2 inclusive. And then for cosine, the restriction was 0 to pi inclusive. And then tangent, I'm just going to do this. Tangent, it was negative pi over 2 to pi over 2, but now it's exclusive. Negative pi over 2 to pi over 2 exclusive. But that's all we really need. So everything is still the same. Let's try an example. All right, so let's try to evaluate sine of tangent inverse of 1/2. And we'll do this one together. I'll do this example and then you can try the next one on your own first. But one thing I want to point out is that in section 6.1, we never saw expressions like this. What we saw in 6.1 was sine of sine inverse. And then you would have to think about the restricted domain, et cetera, et cetera. But now we're doing sine of tangent inverse, sine of tangent inverse. So how are we going to do that? Well, we need to remember what tangent inverse is. So tangent inverse of 1/2 is the angle that has a tangent of 1/2, right? So it's the angle whose tangent is 1/2. But now we have a reinterpretation of what tangent is. Tangent is opposite over adjacent, SOHCAHTOA, right? So you got to remember SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. Tangent is opposite over adjacent. But because tangent is 1/2, we know immediately that we have a right triangle where the opposite leg is 1 and the adjacent leg is 2. There we go. Okay, now that we know that the lengths of those two legs, we can solve for the length of the hypotenuse using the Pythagorean theorem. So you use the Pythagorean theorem, you find that this length is going to be √5, and now we ask ourselves, what is sine of this angle theta? And that's pretty much it. That's pretty much it, right? Because remember, sine is opposite over hypotenuse. And now because we have all three of the lengths of the sides, we can easily just compute sine by looking at the triangle. So sine of theta is opposite over hypotenuse. So looking at these angles, you can clearly see we're going to get opposite over hypotenuse. So sine of tangent inverse of 1/2 is 1 over root 5. Easy peasy, right? Easy peasy mac and cheesy, like my kids like to say. But there it is. So it's very, very easy to do when you have right triangle trigonometry. So that's one of the reasons that I wanted to save it for after section 7.1. Now you try the next example. So here, let me put this one up. I'll throw up the thinker and the speaker and the doer. But yeah, think about how you would solve this one. Think about it for a minute first. All right, now say something out loud to yourself about how you would approach this or something that you would use. Okay, now you try it on your own. Think about the example we just did and see if you can find the exact value of cosine of sine inverse of negative 1/3, and then we'll do it together. All right, here we go. So how do we begin? Well, we remember what sine inverse is. So sine inverse of negative 1/3 is the angle whose sine is negative 1/3. So we'll start with that. The angle whose sine is negative 1/3. And we want to know cosine of that angle. Well, since here the sine value is negative, excuse me, uh, based on the restricted domain that we use to define sine inverse, we're going to have this. Oops, sorry, this right here. So remember, sine is restricted to negative pi over 2 to pi over 2. So that means that the opposite leg of our triangle is going to be negative in, well, I wouldn't say length per se. It's going to be a negative displacement, you could say. So we're going to label the opposite side as negative 1 and the hypotenuse as 3. There we go. So sine is opposite over hypotenuse. Now that we know the lengths of these two sides, we can use the Pythagorean theorem to solve for A. There we go. So use the Pythagorean theorem. You'll be able to find that the length of this leg, the signed length of this leg is 2 root 2. Now that we have all three sides, we can easily calculate cosine of the angle theta. So sine inverse of negative 1/3 is the angle whose sine is negative 1/3, and cosine of that angle is adjacent over hypotenuse. So that's going to be 2 root 2 over 3. And that's the answer. Yay, right? Not too bad. Not too bad. Construct the right triangle, find the missing side, and then just evaluate it using SOHCAHTOA, and you're done. Okay, let's do another example. So this is another one you should try on your own first. Try to evaluate tangent of cosine inverse of negative 1/3. And as an initial hint, think about what your triangle is going to look like based on the restricted domain of cosine, all right? So try this one on your own, and we'll do it together in just a minute. All right, here we go. The approach is pretty much the same as the last few examples. What's nice about this is it's always the same approach. Cosine inverse of negative 1/3 is the angle whose cosine is negative 1/3. So based on the restriction for cosine, I'm going to construct a right triangle that has side lengths 1 and 3. I'm sorry, a leg length. Well, I'll just show the picture. Here we go. This is what the triangle is going to look like. And one thing I want to emphasize here is the reason the triangle is oriented this way is because of the restriction to cosine. So remember, cosine theta is between 0 and pi. So that's why our triangle is tilted this way, or sorry, tilted this way, right? Tilted this way. Am I doing it right? Yeah, that's right. And that's why the lower leg has a length of negative 1, because it's basically in the negative direction from the north-south line, you could say. So cosine of theta is negative 1/3. but cosine is defined as adjacent over hypotenuse right here. So that's how we get that triangle. Now that we know the length of one of the legs, or the signed length of one of the legs, and we know the length of the hypotenuse, we can solve for the length of the remaining leg, and we'll get 2 root 2. So now we have all three of the leg lengths, including their sign, their direction. So what's tangent of cosine inverse of negative 1/3? It's tangent of this angle that we've depicted with the right triangle. What's tangent? Tangent is opposite over adjacent. So the tangent is going to be negative 2 root 2. Boom, and that's it. It's fun, right? So to be honest, this section on the homework even is really just doing this a lot of times. And again, remember it when you get to Calc 2, because this is really all you're going to do if you have to evaluate these like compositions of inverse functions and their standard functions. And if you ever have information about two parts of a triangle, you can get information about the whole triangle, and that helps you figure out all these relationships. It's just a really, really handy tool. Okay, one more example, and then that's actually it. So you try this one on your own as well, and then we'll do it together. Write sine of tangent inverse of u as an algebraic expression in terms of u. And just a reminder, an algebraic expression just means you don't have any trig functions involved. You've only got stuff that's like numbers and square roots and powers, that kind of thing, but no trig functions. So think about it for a minute and then try it on your own. All right, now let's do it together. Same process as before. What is tangent inverse of u? That is the angle whose tangent is u. So since tangent is opposite over adjacent, right here, we can write tangent of this angle theta as u over 1, and we can construct a right triangle with that relationship, u over 1, as the opposite over adjacent. There we go. Now we use the Pythagorean theorem to solve for the hypotenuse, and we find that the length of the hypotenuse is going to be square root of 1 plus u squared. Now that we have all three parts of the right triangle identified, all three legs, I should say, or all three sides, I should say, we can compute sine of this angle theta. So what's sine of tangent inverse of u? It's sine of theta, but sine of theta is opposite over hypotenuse, which is going to be u over square root of 1 plus u squared. And there we go. There we go. Done. That's it. So that's an algebraic expression involving u. There's no trig functions involved anymore. And so that's it. And that's it for this section. Like I said, this section really isn't so bad. You just need to know a little bit of right triangle trigonometry. But now that we've got it, you can do these questions like cake mostly. Just drawing those triangles, looking at the triangles, and then evaluating what the trig functions are going to be using SOHCAHTOA. Oh, I didn't include an example in this lecture here, but even for the reciprocal functions like cosecant or secant or cotangent, the process is the same. You just remember that, for example, cotangent is adjacent over adjacent over opposite. But the procedure is the same. You're just going to reciprocate your results. All right? Okay, so I'll stop rambling. Thank you all again, and I will see you next time.